So, yeah, as he said, I'm looking at the evolution of colour vision in trilobites. So, there are two lineages in the animal world that developed colour vision, and those are the vertebrates and the ecdysozoa. More particularly, we know in the arthropods, but we don't really know that much about these four, which are the myriapods, centipedes, the nematomorphs, the horsehair worms, the chinorhynchs or mud dragons, and the penis worms, the Priapuliida. Because nobody's really done much study on whether or not they have opsins in the first place. Opsins are a light receptive protein. If you have more than one type of them, then you can see in colour. You've got the onychophorans and the tardigrades, which have one each. The insects and the chlysterids have a lot more variation from piece to piece, but I've picked a yellow weaver spider and a swallowtail butterfly there, and they've both got 6. The crustaceans can have some really odd outliers. That's a mantis shrimp, which has 16 opsins. That's the equivalent of kind of trying to see in 16 primary colours. It's quite a different visual environment. So we can use this to try and recreate the visual environments of extinct animals, like Anomalocaris or trilobites. And the way that we do this is by using a gene duplication tree. If a species sits on the tree, like say let's assume species 5 is extinct, but we know that it occurred after the gene duplication event, then we can reliably assume that it possesses both the alpha and the beta opsin, so it could have seen in colour. Because we can bracket it with later and more basal taxa. Now, what we've got here is the onychophorans, the tardigrades, Anomalocaris, chlysterids, and trilobites. So trilobites sit between what was known as the mandibulata here and the chlysterids. And Anomalocaris sits between the arthropods and the rest of the ecdysozoa. So, what have I found? Well, for a start, the onychophorans sit outside of this massive arthropod opsin clade. So we can't actually tell you whether or not Anomalocaris saw in colour. I'm very sorry, I've misled you a bit. But what I can tell you is that the last common ancestor of the trilobites and the rest of the arthropods, at the very least, had 4 colour opsins. They saw in UV, or they had an RH7, which is an unknown ultraviolet sensitive opsin of some kind. They saw in blue. They had a visual opsin they co-opted to regulate their diurnal rhythm processes, and they could probably see in green and red as well. And also, I've got a bit of a treat for you, which is something I found out only the other day, which is, if we consider this, there are also 6 more putative sites that if I get a hold of a myriapode, I can probably cut out a few more, and also if I date these using a molecular clock, I can probably get rid of a few more possible sites. I doubt they had up to 10, but they probably possess some of these sites here, which are more ultraviolet sites, which are very useful in water, and another green-red, low-sensitive site. And a little final note, that's a limulid, and all of the limulid opsins, the horseshoe crab opsins, cluster there, which makes them really weird, because they seem to have, so the limulids that I've got, Limulus polyphemus, seems to have an ancestor that went down to 1 opsin, and then the more recent limulids have decided, no, I want to see in colour again, and have decided to see in colour again. And I'd like to thank Davide Pisani, my supervisor, Nick Robertson, Ronald Yena, who have also been helping me as secondary supervisors, and NERC for the DW4 GTP for funding my research. Thank you. Any questions?